Modern advanced driver assistance systems operate flawlessly on well-lit, clearly marked highways. But when a vehicle encounters the edge of its operational design domain, like a blinding, dense fog bank, these systems routinely fail, requiring immediate human intervention. Adverse weather, such as heavy rain, snow, and fog, does not merely obscure the road. These conditions physically alter how electromagnetic waves and light behave, corrupting the incoming sensor data before the software even begins to process it. Moving from Level 2 driver assistance to Level 5 full self-driving requires abandoning simple, rule-based PID controllers. Hard-coded logic cannot account for corrupted data, requiring deep learning models capable of predicting outcomes when the inputs are compromised. Engineering a specialized algorithmic architecture using multi-sensor fusion and targeted datasets is the only way to resolve these edge cases. Physical hardware degrades predictably in severe weather. The solution to Level 5 autonomy is therefore strictly mathematical, building software capable of compensating for the inevitable physical limitations of the sensors. The perception baseline of a modern autonomous vehicle relies on three distinct modalities. Cameras provide high-resolution visual texture and color. LiDAR emits laser pulses to map precise three-dimensional depth. Radar uses radio waves to measure velocity and penetrate precipitation. But each modality has physical limits. In heavy snow or rain, LiDAR pulses reflect directly off airborne droplets. The sensor registers these as solid objects, flooding the point cloud with false phantom obstacles. Falling snow reduces camera contrast, while heavy precipitation causes severe radar wave attenuation, shrinking its effective range. Because every sensor type possesses a critical physical vulnerability, no single modality can reliably interpret the environment at the edges of the operational design domain. This physical vulnerability necessitates multi-sensor data fusion. Hardware redundancy provides no safety if the software cannot cross-verify inputs to filter out environmental noise. Fusing this data introduces a severe software bottleneck. Engineers must balance the computational load of processing complex environments against the requirement to execute those calculations in real time, often exceeding 100 frames per second. This graph plots the performance of object detection algorithms, tracking average precision against the total parameter count in the model. Lightweight models like YOLO V8 are efficient, but their accuracy plateaus at roughly 56% average precision. Algorithms like point fusion break this plateau. By projecting the 3D LiDAR point cloud onto the 2D camera matrix, the system cross-references data to filter out false positive detections. The industry is now deploying vision transformers and deep fusion models to capture long-range contextual dependencies. These architectures map complex relationships across the entire scene, though they demand significantly higher compute power. Filtering hardware-induced errors in real time requires immense computational complexity. High parameter counts are the mandatory price for maintaining an accurate environmental model in adverse weather. A multi-sensor fusion model is only as robust as its training distribution. If the model has never encountered a specific chaotic edge case during training, it cannot reliably navigate it on the road. Standard datasets like NewScenes provide over 1 million images of highly structured urban environments, usually in clear daylight. There is a severe lack of available real-world data for extreme blizzards, dust storms, and dense fog. To bridge this gap, engineers use generative adversarial networks, or GANs. These neural networks take standard driving footage and synthesize photorealistic edge case data, converting a sunny street into a violent blizzard or a dense dust storm. Specialized datasets like WEDGE utilize these GANs to simulate weather permutations that are difficult to capture manually. This provides the data necessary to train models that remain robust in the face of rare environmental extremes. Achieving full self-driving relies on algorithmically synthesized simulated environments just as heavily as it does on miles driven in the real world. Mapping the static environment is only the first step. The vehicle must also calculate the non-deterministic dynamic behavior of the humans sharing the road. Simple if-then logic fails when human actions deviate from expected patterns. An autonomous vehicle must react to irrational behaviors, such as aggressive lane changes or a pedestrian stepping blindly into traffic. Engineers use long short-term networks, specifically social LSTM, to track these movements. The algorithm analyzes the velocity and social interactions of every object in the scene, generating probability vectors projecting a pedestrian's future path. Within milliseconds, a model predictive control system calculates a safe, evasive trajectory that routes around the pedestrian's highest probability future locations. Reliable autonomy demands that the system continuously calculate and optimize for the immediate future, rather than simply recording the road's current state. The Level 5 architecture integrates hardware redundancy, cross-modal point fusion, GAN-augmented training data, and LSTM-based behavioral prediction to execute complex evasive maneuvers in blinding fog without human input. Advanced driver assistance systems rely on clear environmental conditions and human oversight as a safety fallback. Full self-driving systems operate on the opposite premise, an assumption that hardware will fail, weather will degrade, and human behavior will be irrational. The future of autonomous engineering is no longer focused on perfecting the sunny highway drive. Level 5 autonomy functions as a demonstration of algorithmic mastery over the real world's most chaotic edge cases, moving beyond the capabilities of mere automotive hardware.